take out a sheet of paper. We're going to be taking a quiz, right? Every Friday we take a quiz.
Can I ask a question and quiz over?
Pardon me?
I didn't have any homework this week.
You didn't have any homework this week?
9.3 on Monday, 9.3 it? Yeah.
We already got through 9.4 as well, right?
I mean, we learned about it, but it's due on Monday.
It's due on Monday? Okay. So last time we had a quiz about like section 1 and 2, right?
I think so, yeah.
Maybe we should have a quiz today about section 3 and 4. Is that okay with you guys?
Sounds nice.
I mean, haven't done 4 yet, but sure.
You haven't done 4 yet? So I'll just keep it about just 3. Section 3. Is that fair? Okay, good. You guys may think I'm the one here in charge with authority, but I believe it's you guys who is in charge with authority. Okay? Really, I want you guys to like run this the way you want. Of course, you can't, have like pizza parties every day and have you swinging off of the ceiling. But yeah, seriously. I want you guys to learn, have fun, and enjoy math. And realize it's not just something you have to do, it's something you love. You wake up in the morning and you're like, I can't wait to do math. Okay? So, quiz. So let's see. Let's say this is the ground. We have a wagon. And someone is pulling this wagon at an angle of 33 degrees with a force equaling 40 newtons. Okay. If they displace a total, if the person moves the wagon from point A, which we can set as 0, of course, it's like kind of 0, comma. We can set the origin at A, so it's 0, 0. And it moves over here to B. Let's say it moves 100 meters. How much work was done? That's number 1. Number 2, let's say. Second one is to find the angle between these two vectors. Yes, ma'am.
Are we allowed to use our calculator?
Yeah. Yeah. Yeah, and let's say you don't have a calculator.
I was thinking, when you still need to buy batteries for yours.
Yeah.
Right, okay. You don't have to find the decimal. Just have it set up to where you're about to put it into the calculator and box that. That will give you 100% credit. Okay? I'm a mathematician over here. All right? We mathematicians, we play by the rules that we've created. And yeah, mathematicians have basically created everything. two questions on this quiz isn't that bad, right? I'll give you guys 10 or 15 minutes to do it. Yes.
What's that angle? I can't remember.
Oh, I'm gonna make it bigger. It's 33 degrees. And I'll make it in yellow. Cause I got some new chalk up in here.
We have more colors?
Cause I got some new chalk up in here.
That's crazy.
So there's about 1 minute remaining. Kind of finalize your thoughts and put down as much justification for your work as possible to receive partial credit. Is today? Yeah, it is. It is the 28th. Okay, pass them on up. And while you do that, which one of these colors stands out the most to you? Which one you want me to use today?
I'm good for orange and yellow.
Orange and yellow?
I like red.
You like red? So we got orange, yellow, red. Is there any other one? I guess they're all good, huh?
They are really okay.
Okay. Thank you. Thank you. Appreciate it. Okay. Well, I'll just start off at random. I'll use any of the colors. Okay. So let's talk about planes being parallel. We talked about planes, and we talked about this being a scalar equation for a plane. Right? That's the scale. Can you guys see that? You can't see it? Blue isn't that great, huh? Let's try orange. Scalar equation for a plane. How's this? Is that better? Stands out more? Nice. Okay. So in general, that's your scalar equation for the plane. And notice that our normal vector is this. And this is due to the fact that, remember, n dot r should be equal to n dot r naught. This is the scalar equation of the plane. This is the vector equation of the plane. Whenever you do the vector equation of the plane, do the dot products here and here, you will derive something like this, where d is going to be equal to negative ax naught minus negative by naught minus negative c z naught. Once you go through the derivation, that's what d is really set equal to. So now let's talk about two planes. How do we determine if two planes are parallel? Well, two planes are parallel if they're scalar multiples of each other. Specifically, if their normal vectors are scalar multiples of each other. So let's do an example. Let's say plane 1 is equal to x plus 2y minus 3z equal to a 4. And plane 2 is equal to 2x plus 4y minus 6z is equal to 3. Okay. Let's see if these planes are parallel or not. We notice that they're normal vectors. This implies that the normal vector for plane 1 is the coefficients of the x, the y, the z, and this implies that the normal vector for the second plane is the coefficients of the x, the y, the z. And the reason for that is it's because you take the dot product of n and r respectively. Remember r was defined as just x, y, z. And when you take the dot product between n and r, you get this, ax plus by plus cz. So whenever you have a 1 here, a 2, 3, and a negative 3 here, this was a consequence of a dot product, meaning one of the vectors in the dot product was 1, 2, negative 3, and the other vector in the dot product was just x, y, z. So that's where that comes from. Now, we notice these guys are parallel because notice that n2, the second normal vector, is equal to scaling the first normal vector by 2. If I multiply this vector by 2, this becomes a 2, this becomes a 4, this becomes a negative 6. So if their normal vectors are scalar multiples of each other, that implies that they are parallel. Okay? So in general, you remember that we have the parametric equation, but we also have the symmetric equation where you have x minus x naught over a is equal to y minus y naught over b, which is equal to z minus z naught over c. These are the symmetric equations, right, for a plane or a line. This is actually for a line, not a plane. This is the scalar equation for a plane. These are the symmetric equations for a line. But notice that two planes, when they intersect, what is their intersection? Yeah, it's a line. When two sheets intersect, they intersect and that intersection forms a line, right? So that's why we're bringing up the symmetric equations of a line here. What you can do is, in general, you can define how two sheets or planes intersect. The line that they form can be, in general, attained by saying this is equal to this, and simultaneously, why is it that we set it equal to the y? It's arbitrary. We could have set it equal to the z. We could have set this equal to z and y equal to z. It doesn't matter. It's just we want to go back to our old days of saying y equals mx plus b. And here's what I mean by that. Notice that this equation right here can actually attain the form y equals mx plus b through some algebraic steps. So if I multiply both sides by b, I get b times x minus x naught all over a is equal to y minus y naught. Then this is equal to b over a times x minus x. Actually, I'll distribute that b over a. So I get b over a x minus b over a x naught. And then I'm going to add that y naught, because why not? So now take a look. This is a constant, constant, constant. This is the only variable, right? So I can set this whole thing equal to some b. I'll define that to be equal to b. So then I have y is equal to, one last thing. I can define b over a to be m. So then this equation reduces to y is equal to mx plus b. You guys see that? That's why we can get a line out of this situation. Out of the planes, we get a line. And look, it reduces to the linear equation y equals mx plus b. Okay? That's all we have time for to talk about in that section. 9.5. Now we move on to 9.6. Okay. And I will note that this has a, so we're going to take a test over all of chapter 9. 9.6 and 9.7 are the remaining sections. So today we should be getting past 9.6. Monday, 9.7. And Friday, a week from today, you should be expecting for your first test. And I know what you're thinking. Where's all my feedback on my assignments? You should be thinking that, okay? So what I'm going to do this weekend is make sure that I grade almost all. My goal is to grade all. Unless some type of like tragedy occurs in my life, you will get all of your assignments graded and handed back, and I'll put solutions to all the homework problems that I've assigned you so that you have that to study for the exam on Friday, a week from today. Sound good? Yes, ma'am.
Dr. Dole said we became doing lab.
Oh,
So correct.
yeah, that's true. I forgot about that.
I don't
Oh,
like say something and be wrong.
right. So what we might do, since we wouldn't have reached, well, yeah, if 9.6 is today, 9.7 is on Monday, and your lab is on what day?
Wednesday.
Okay, so that's possible, right? Okay, well, let's shoot for then on Wednesday. If that is not enough time to absorb it, we might push it to the next week. And what I'll just do is I'll just like continue lecturing on the rest of the chapters while you guys are preparing for the exam next week. I'll see what's going on. Maybe that might not give you guys enough time to absorb the feedback that you've been given, right? So let's tentatively plan it for this coming Wednesday, but I have in mind that that might not be enough time, and I will extend it to the following Wednesday, if necessary. Okay? Yeah, I'll do it. I'm not going to make any promises, but chances are I might. Chances are I might not. Prepare as if it will be on Wednesday. That way, if you have another week, then you're extra prepared, right? Okay. Let's move on to 9.6, functions and surfaces. Okay, typically we call R2. This is really the Cartesian product of R cross R, meaning this is defined as a set of all x, y, such that x is in R and y is in R. This definition kind of seems dumb, but if I label this the first reals and the second reals, then you could see, oh, okay, so they're distinct, they're different. But this R and that R is the same reals. This is just a copy and it's different. And it's perpendicular to the first one, of course. Okay, so function f of x, y equaling some z. Let's define this. So this is a function that maps R cross R onto R. Meaning it takes an f comma y equaling z, where x comma y, and actually maybe I should say it takes an f of x comma y and maps that onto z. Okay. But you'll actually, in your book, you will see it denoted like this. But it's technically this, right? I like it like this, because this is what it technically is. Okay, parentheses matter in math for sure. So now, what we're going to be doing is basically getting, before we had one input, one output. F of x is equal to y. One input, x, one output, y. Now we have two inputs, one output. Two inputs, one output. Your book states that an example of that is like, imagine the surface of the earth. And it says that we can define a temperature on the surface of the earth given a longitude and a latitude. Yeah, right? Because any location on a sphere can be given by a longitude and a latitude, right? So the temperature on the surface of the earth is a function of two variables where x is the longitude, y is the latitude. So we can assign to a pair of longitude and latitude a temperature. That's an example of a multivariable function, a two-variable function. Okay. So although now this is the first time you guys have been introduced to multivariable functions. That's because this class is multivariable calculus. And so this is two-dimensional calculus, and we're going to move on to three-dimensional calculus. Okay, but things are all the same. This is still the domain. This is still the range, just like usual, right? It's still the domain and range. It's just your domain, as opposed to how you've been doing it, had one entry. The range had one entry. The domain now has two entries. Why did we do this? Because certain things are more usefully described this way, like the temperature being at a longitude and a latitude. Notice that if you just only had a longitude, then you would be talking about the temperature on a great circle about the Earth. Let's say the equator. That's the biggest circle you can form around the Earth. But you wouldn't know where on the equator. Is it over here in Ecuador? Is over here in sub-Saharan Africa, is over here in the Pacific Ocean. Who knows where it is? You have to say, okay, it's at this latitude, but also at this longitude. So let's talk about an example function. What about f of x, y is equal to x squared plus 4y squared? What is its domain? Well, just like with normal functions, let's just go back to normal functions here. What is the domain of f of x is equal to x squared? Yes. Negative infinity to infinity. And why do you say that, Alexis?
Because it's a parabola, but it extends in the positive direction all the way to infinity, and at the opposite, it extends all the way to negative. There's no stopping point.
Yeah, so the domain is the set of input values that doesn't mess the function up. So remember, what about f of x is equal to 1 over x? What's the domain of this function?
All positive.
All positive numbers? So I can't plug any negative numbers in here? You can, okay.
All non-zero.
All non-zero numbers?
Yeah.
Oh, right, because when we divide by 0, that's bad. Have you guys ever been shown why you can't divide by 0?
Yeah.
Who?
Using limits, you approach two different things.
Oh, yeah, that's the limit way. Here's the actual proof, real quick. Let's say 3 over 0, what do you want it to equal? Assume you can define that.
1.
1. Multiply both sides by 0, I get 3 is equal to 0 times 1, which is 0, which implies 3 is equal to 0. Contradiction. If you're then think about it, well, what about anything divided by itself is equal to 1? Then 0 over 0 should equal 1, right? It should, but look, multiply both sides by 0, Cancel the 0 over here. I get 0 times 0 is equal to 1 times 0. But that equals 0, so there's no contradiction. You should 0 over 0 should be equal to 1, right?
What's the indeterminate?
No, yeah, no. We
And
can,
also you can set the other things equal to each other, yeah.
yeah, we can prove it without calculus. Notice that what happens when I add a 0 to both sides. So this becomes 0. This is 1 times 0, not 0.0. 1 times 0, and I'm going to add a 0 to both sides. So I didn't change anything, right? So this becomes 0, and I can factor out a 0 here. So this becomes 1 plus what? The whole concept of factoring is I factored out a 0 here, right? But notice that when I factor out a 0 from here, 0 times 1 is 0, which restores this. 0 times something is 0, right? But 0 times any number is 0, right? Unless it's infinite. 0 times any finite number is 0. So I'll put an n here. Because that's true. Logically, it can be any finite number. Okay? Notice that when I divide by 0 now, I get 0 over 0 is equal to 1 plus n. Notice that by hypothesis, we assumed 0 over 0 was equal to 1. So we get this equation here. But notice, yes, if I pick n equal to 0, this equation holds. But if I don't pick n equal to 0, let's say I say n equals 2, then this equation implies that 3 is equal to 1. Contradiction. That's why you can't divide by 0. Just a logical argument, no limits involved. Limits work too, but this is another argument. That's why you can't divide by 0. It's because it will destroy mathematics. It will no longer make math logically consistent. You get things like 3 equals 1, 8 equals 1, stuff like that. We don't want that. But anyways, back to domain. You discovered that the domain of 1 over x is this. You discovered that the domain of f of x is equal to x squared is equal to this. So we can agree that the domain is a set of inputs that when we plug it into the function, nothing messes it up, right? So again, like f of x is equal to square root of x. What's the domain here?
All non-negative numbers.
All non-negative numbers, right? 0 included to positive infinity. We don't want the negative ones because then we'll be doing complex analysis, not real analysis. Okay, so now you get what domain is in the single variable. That easily translates to the 2 variable version. What's the domain of this function? What?
Positive, negative.
Yes. Why?
Oh, well,
Actually, let me write out the real domain. It's this. Right?
oh, for x and y.
Yes.
Just fix math that.
Yes.
You have 1 for an x.
Yes. Because the domain of x squared is all real numbers. The domain of 4y squared, all real numbers. But what if I had something like this? F of x, y is equal to 1 over x minus 2 over y. What's the domain of this function?
X equals down 4. So the negative infinity to 0. 0 to negative infinity.
Union 0. Oh, wait, positive infinity here. But this is multivariable domain, right? So actually, let me move this over here. We don't need this dividing by 0 stuff anymore. Yeah. This is why you can't divide by 0. You guys have gotten to calculus and still haven't seen this. I mean, I show this to pre-calc 1 people because they can understand it. It's just algebra. Okay, so now I have more room. The domain, I'm just rewriting what you said. Okay, that's this part. Cross This was for X. What's it for Y? Same thing. What about this? What's the domain of this function?
Still 0 again for the X, but then the other will be.
You mean negative infinity to 0, union,
Yeah.
0, positive infinity,
Yeah.
cross,
And then just 1 to
1. Oh,
It can't be 0.
well, it can't be 0 itself, because then you're dividing by 0. But couldn't it get close to it infinitesimally? Technically, yes, right? So it'll be 0, not included. Positive infinity. Right? I can take 1 over the square root of 1/2. I can take 1 over the square root of 1/4. 1 over the square root of 1/4 would just be 1 over square root of 1 over square root of 4, which is 1 over 1 over 2, which is 2. So that's definable. We can plug in a fraction into that, and it outputs something that doesn't mess up mathematics. You guys seem to be enjoying yourselves, and I'm enjoying that. Very good. Okay, so you guys are gonna have to like do this for your homework and for this section. All right. So once you talk about domain, then we can talk about graphs. Okay. We have a 3-dimensional surface here. Okay. This 3-dimensional surface, X, Y, Z, the points, let's say this is a point. This is the set of X, Y, Z. But notice we can also define it as an X, a Y, and an F of X, Y. Because we denote F of X, Y. F of X, Y is typically denoted as being equal to Z. So before we had F of X is equal to Y. But now Y is being involved with the domain. So we just demote it and promote Z. If we go to 4-dimensional math, Z would then get demoted, and we'd pick a new thing, you know, M. But we're not doing that. We're not doing 4-dimensional math. We only go to 3 dimensions, and that's it. I know, right? Einstein's theory of gravitation says that we are in 4-dimensional hyperspace time embedded in 5-dimensional hyperspace time. So that mathematics surely does exist.
Oh, that's without even.
But we won't be doing it here. But I wish we could. So let's talk about a 3D surface. So what about F of XY is equal to, let's say X squared. Let's something really simple. This is equal to our Z, right? Z is equal to X squared is another way of saying that. Well, what does this form? Well, it's just like F of X is equal to X squared. As Alexis pointed out, it forms parabola. It forms parabolas, plural. It forms a parabola in 2D, just one. But in 3D, you get that one parabola and you smear it forward and you smear it backwards. So it creates like a folded piece of paper shape, right? Infinite, and here and there, okay? So it looks kind of like this. I'm not an artiste, all right? Like them dudes with the funny hat and the palette, not that. But the book is beautiful, and Maple, you guys have access to Maple. You guys can graph 3-dimensional functions, and they look really, really sick. They look really, really tight. You young kids use those phrases: sick, tight, cool, dope, stuff like that, right? It looks really dope. I mean, this is when math gets really cool, is when you start talking about three-dimensional shapes. I mean, geez Louise. If we introduce this to little kids, they would love it. Instead of like, y, find x, solve for this. That stuff is essential, but also you need to show them some more exciting stuff. So f of x, like 4x squared plus y squared. This forms an elliptic parabol. Oh wait. Yeah, an elliptic paraboloid. This is in your book. Really, it's like a two-dimensional, like, it's like a bowl. It's like a bowl. It's like a plot. It's a pot. It's a pot you plant pots in. Plant pot. So you can go into your textbook. I can't write out all, well, I could write out all the equations, but really this section, the main concepts in this section are, what is the function of two variables? What is the domain? What is the range? We didn't even talk about range, okay? So for instance, let's talk about like f of x equal to x squared plus y squared. We know that the domain is all real numbers. What would be the range?
All around.
Really? Even the negative ones?
Well, actually no, because you can put those in.
Right, so the range, yeah, when we square a negative number,
Yeah, I forgot there.
yeah, so the range should, so the smallest this can get is 0, and we'll include it. But that's it, then it goes to positive infinity, right? So make sure you play with that concept as well, the domain and the range. So the main concepts in this section are domain and range. There's graphing. It's no different than the graphing you've been doing, except it's three-dimensional. So what they do is they say, do a method of tracing. What I did was I traced one parabola, then another one, then another one. Because in 2 dimensions, this thing gets squished, and you just get one nice little shape. But in 3 dimensions, we have to pull it out. Pull it out, it comes out of the board, it comes out of your pieces of paper, and it goes into your pieces of paper, and it's very cool stuff. Math gets real heavy, and it's really cool. It gets more complicated, and it's really awesome. Okay? So you can go through your text, and you guys have Maple, and you can do all kinds of equations and make all kinds of different surfaces. And you should get familiar with what equations give what surfaces. So, for example, x squared over a squared plus y squared over b squared. Let's make my y not look like my b. Plus z squared over c squared. Let's have that equal 1. Okay. This is an ellipsoid. An ellipsoid is a common shape we see on ESPN. It's the football. Woo! Football. Let's tackle. Knock that jug out. It actually, football is an ellipsoid. So an ellipsoid looks like this shape. I played linebacker for a year, so.
While you were in college?
No. High school. My mama made me quit after freshman year of high school. Yeah, that's okay. It's not a big deal. She also wouldn't let me become a cage fighter.
What?
I know. I would have been in an octagon instead of in front of you teaching math. Okay. So actually, I'm okay with that. I've come to terms with that. It's okay. So this is an ellipsoid, right? It looks like a football. But notice that here's the really cool part. If A, B, and C are the same, the ellipsoid morphs into a sphere. A equal B equals C. This implies this equation can just be reduced to x squared over A squared is equal to y squared. Oh no, x squared over A squared plus y squared over A squared plus z squared over A squared is equal to 1. Notice that we can factor out an A squared, 1 over A squared, that is. So I get x squared plus y squared plus z squared is equal to 1. Multiply both sides by A squared, you attain a sphere of radius A, right? Centered at the origin. So the ellipsoid and the sphere are the same, kind of. A sphere is a special case of an ellipsoid, right? It's like you have this deformable football, and you can squeeze it and turn it into a sphere, or you can stretch it out and turn it into a football-looking shape. That's why this stuff is really cool, because this three-dimensional math can now describe things in real life that we interact with. Our world is three-dimensional, spatially, for what we know. Some people in theoretical physics who study string theory believe that we live in 11-dimensional space with 1-dimensional time, so 12-dimensional hyperspace time. That's what they believe. I disagree, but they have created extensive theories based off of the fact that on the quantum mechanical scale, when you zoom into space and time, into reality, very, very, very far zoom, that space is no longer three-dimensional, that it attains more and more spatial dimensions the more you zoom in. I personally believe that is a load of baloney, because they're just adding more spatial dimensions to help them with their mathematical calculations. And although that's useful in doing the mathematical calculations, there's no way to test that theory scientifically. To be able to test string theory, we'd have to create a large hadron collider that had the circumference of the entire Milky Way galaxy in order to generate enough energy to find a string. Chances are we're not doing that in our lifetimes, right?
Not with that attitude.
Huh?
I said not with that attitude.
No, actually, the right attitude is to be like, you know what, this theory is virtually untestable. Let's work on other theories. Let's not assume that the space is 11-dimensional. Let's assume that it's still 3-dimensional, with the fourth dimension being time, and let's create a different theory besides string theory. Let's let them have fun being highly intelligent morons. Okay, plan on your test being on Wednesday. Okay, and if I'm feeling nice, I may extend it. I have to talk to Dr. Zoller about that. We'll see what happens. Yeah, but what I'll try and do is I'll try and get the feedback uploaded as soon as I can and email you guys when I do. But if I see it's not enough time, it's not fair, you best believe I will extend it. Because I want it to be fair. I want you guys to have the appropriate time to be able to prepare. Yes, sir. Feel free to use any of the colored chalk that I have now.
It's a very cool chalk.
Yeah, I know.
Oh, this feels nice.
It's different than any chalk you've ever touched before. This is Hagoromo brand chalk. It is the Rolls Royce of chalk. The Benz, the Mercedes-Benz, the Bugatti of chalk right here is in your hands right now.
I was thinking about when you were drawing the shape like
Yeah, the
this.
traces, yeah.
Yeah.
That's a
So-
much better drawing than what I had. Good job.
So in Calc 2,
Uh-huh.
we calculated surface area.
Uh-huh.
And so for 3-dimensional space here, how would that change?
It
Because
wouldn't.
Well, because the math basically was, or the math that we used in Cal 2 was for 3-dimensional objects.
Yeah, well, first you take the parabola and then you integrated it, right? to calculate surface area.
Mhm.
So the surface area should be the same. Even though you started, so when you take the integral, what are you doing is you're increasing the power, right? So let's say I have a length. Let's say I have an area, and then let's say I have a volume. I should just let you draw all my shapes, but so notice this is like an x, this is an x squared, and this is like an x cubed. So what you did is you took your two-dimensional entity, integrated it into your one-dimensional entity. It's actually just a straight. It's not a straight line, but it's a curve, right? Which is we can extend it and straighten it. You took your one-dimensional entity, integrated it into a two-dimensional entity, and you found the area. So yeah, actually, it wouldn't matter whether this area was living in 2 dimensions, or if this area is now living in 3 dimensions. If I were to somehow stick this slice inside this cube, the area is the same, right? So it doesn't matter.
Well, because I was just confused a little bit because when we did it with the other integration forms and we rotated it about, like
Yeah,
various
surface of
points,
rotation.
that didn't involve any sort of z-axis.
Right.
It was more conceptual in our heads of we rotated it so it's now 3D, but we described it only using terms of x and y.
Right.
So,
That's right.
So how would this also only be described? Because it is 3-dimensional, so it does have a z
So
function.
Yeah. I mean, it goes back to this thing. F of x, y can be defined to be equal to some z. Right. You're right though. There was no z involved. You were just talking about. And here's why z wasn't involved. Okay. The way you do that rotation problem is you don't have the 3-dimensional structure and you calculate its volume. That would require 3 dimensions. You have the 2-dimensional structure and you calculate all of the infinitesimal areas that add up every time you rotate it, right? So you add up all the sheets, all the cross sections until you rotate it fully. You add all that area up and you say that forms a volume because I kept rotating and kept adding all these cross-sectional areas. And so once I'm done rotating and I come back to my original spot, adding up all those cross-sectional areas should equal the volume. So we were able to calculate a volume without using the 3rd dimension, z.
Yeah.
We cheated.
We just integrated.
Yeah.
Basically infinitely.
Yeah, so we got this shape, whatever shape you have, a parabola, and you just integrate. And what that does, integral is an infinite sum, right? You're summing all of the cross-sectional areas. That's what you were doing. You were summing all of them. And that equals a volume.
And then for that, we wouldn't necessarily need an integration, would we?
You needed the integration to perform the volume.
Well, no, for like this.
Oh,
if
for
we're
this?
describing it in R3, we wouldn't necessarily need
You wouldn't need to integrate.
Yeah, because
you would need
have
a
definitions of all 3.
You need a formula that would be able to calculate the volume, right?
Yeah, well, something from this.
Let's say calculus is not invented. Let's say we're human beings that don't know calculus. Then the only way we would be able to calculate what is the volume of this ellipsoid is if somehow we came up with an equation for it, like the volume of a sphere, 4/3 pi r cubed. Like we would have to come up with that equation, even though calculus can derive it. If we don't have any calculus, then we have to come up with a straight equation that does it. But if we do have calculus, then we can derive it using like first principles. That's why calculus is so beautiful and powerful.
It is very nice.
Yes, it's really cool. Shout out to Leibniz and Newton. Salute, for real.
He said Leibniz first.
Didn't he do it historically first? Yeah. I don't know who did it. It doesn't matter.
The story is really
I don't
confusing.
care.
Yeah.
I don't care.
Yeah.
I just care about the truth.
Yeah.
I don't care about that stuff.
I know, I was just messing.
Yeah, I'm sure the Germans and the English will definitely care.
forever fight each other.
They will fight who we came up with it first, but